Hi everyone, I'm Rohan, and today I will tell you how to make both serverless customers as well as serverless service providers happy with the help of our technique, which we call IceBreaker. It is a technique which uses server heterogeneity to solve the critical issues of serverless computing. So, serverless computing is becoming a very attractive paradigm in cloud computing due to its auto-scaling and pay-as-you-go billing model. One major issue in serverless is that of the cold starts, which happens when a function is invoked, but it is not warmed up in the memory of a server. Thus, it increases the total function service time. Also, keeping functions alive in the memory is costly for the cloud providers, as keeping functions warm consumes a lot of computational resources and thus incurs a keep alive cost from the service provider's side. From the customer side, there is a need to reduce the service time by avoiding the cold starts. And from the provider's side, there is a need to reduce the total keep alive cost. Functions have a varying invocation probability. But the state of the art and the state of the practice techniques like serverless in the wild from ATC 2020, what they do is that they keep functions warm for a specific period of time, incurring a constant amount of dollars per second during the keep alive period. However, if functions have different invocation probability, why should the keep alive cost remain same for all of them? This is the main question. Thus, we designed IceBreaker, which uses heterogeneous high-end and low-end servers. The intuition behind is that functions with lower invocation probability should be warmed up in low-end clusters, and those with a higher invocation probability should be warmed up in high-end cluster. However, now the low-end clusters have lower keep alive cost, and hence IceBreaker reduces the keep alive cost. Also, for a same capital budget or a fixed capital budget, you can buy more number of low-end servers. Thus, you can warm up more number of functions, and hence it can reduce the overall service time. But the main challenge over here is that the low-end servers are slow, and so executing functions only on them will increase the service time of the serverless functions, and the customers will be unhappy. Also, as the invocation probability of a function changes and increases or decreases, there are challenges in determining which type of server to choose for the warm-up of a function, or the transition during the keep alive period, how to choose the type of servers, a low-end server or a high-end server. Thus, we need effort in appropriately predicting function invocations for avoiding cold starts and reducing the overall keep alive cost of serverless functions. So let us see some trends which motivate us to design IceBreaker. First, the question is to ask over here is that whether a warm start on a low-end server is better than a cold start on a high-end server. With our experimentation, we found out that it is true for most of the serverless functions. For about 60% of the serverless functions, a warm start on a low-end server is better than a cold start on a high-end server. This motivates that introducing heterogeneity by having low-end servers might be beneficial for the reduction of both service time and serverless keep alive cost. Now we make the second observation. From the figure on the very left, we see that as keep alive time increases, the number of warm starts also increases with it. This is very intuitive. For example, for 35% warm starts, we need a 10-minute keep alive time. Now from the figure in the middle, we see that on a high-end cluster, if we need 35% warm starts, we incur 52.4 keep alive cost and have an average service time of 4.12 seconds. Now from the figure on the right, we see that if we have a mixture of low-end and high-end servers, then if we have a keep alive cost of 44.1, we can get 65% warm starts and have an average service time of 3.66 seconds. So on the high-end server, the average service time was 4.12 seconds, and here the average service time is 3.66 seconds. And also, we can see that the keep alive cost has reduced from 52.4 to 44.1. Thus, with heterogeneity, we have reduced the keep alive cost, service time, and we have also achieved more and more number of warm starts. For fairness, IceBreaker's design keeps the overall capital budget same for both homogeneous and heterogeneous configurations with which we evaluate our results. By employing low-end servers, IceBreaker increases the overall memory capacity under a fixed capital budget. Thus, in this way, it achieves more and more number of warm starts. With these motivations, we designed IceBreaker, which is a keep alive serverless function warming technique, and it exploits heterogeneity in an unconventional manner. IceBreaker makes its decisions based on a dynamically calculated utility function or a utility score, which we'll discuss in the later slides. Now we begin the design of IceBreaker. In its core, IceBreaker has two major design components: a function invocation predictor and a placement decision maker. The invocation predictor predicts the functions to warm up, and the placement decision maker suggests what kind of server, a low-end server or a high-end server or no server at all, to use for the warming up of the function. Now, before we get into the details of the design, the first question to ask over here is that, what are the suboptimalities of the existing approaches of function invocation prediction? So from the figure on the left, we can see that invocation of a function can have multiple different concurrency levels. The present approaches do not take into account the different concurrency levels that a function can have. Apart from predicting the function to warm up, it is also very important to appropriately determine the number of function containers to warm up so that the service time will be reduced and the number of cold starts will be reduced. Also, with varying invocation concurrency, the present ARIMA or histogram-based techniques are very slow to converge. IceBreaker speeds up the overall convergence. Now, from these, we develop the key insight to the design of a function invocation predictor. If we plot the invocation concurrency of a function, we can see that the invocation concurrencies are quite periodic in nature. And more importantly, the invocation concurrencies have multiple periodic components, which are also called harmonics. So the invocation concurrencies of serverless functions have multiple harmonics. So how to model the different periodic components of the invocation of serverless functions? The answer is very simple, and the answer is the algorithm which we all have studied at some point of time in our undergrad or in high school, which is called the Fourier transform. It is a way of expressing any function as a linear combination of sinusoids. In this way, we form a mathematical representation of a function invocation. From this mathematical representation, we predict the invocation concurrency of a function at a future time interval. In this way, IceBreaker takes into account the different concurrency levels of serverless functions and appropriately predicts them for a future interval of time. Now, how does IceBreaker decides on which server tier, the high-end server tier or low-end server tier, to choose for the warming up of a function? This is decided by IceBreaker's placement decision maker. The placement decision maker relies on a utility score by which it makes all of its decisions. So let's say a function has very high true negative rate of occurrence by the function invocation predictor of IceBreaker. Then such a function will benefit from an execution on a high-end cluster as it has seen more number of cold starts due to its high true negative rate. This is expressed by the term Tn. Similarly, if a function has high false positive rate, then such a function has seen execution in high-end cluster much more than the others. So the utility score should decrease, and it is expressed by the term 1 minus FP. Now, apart from the function invocation predictor performance, the placement decision maker also takes into account the characteristics of the application or the serverless function itself. If a function sees higher speedup on a high-end execution, such a function is given higher priority for a high-end execution and its score increases. Similarly, if the memory consumption of function is more, then it involves more keep alive cost. Hence, for such a function, the utility score decreases, and it is given by the term 1 minus MR. With these, we design the combined utility score of IceBreaker, which determines a dynamic cutoff by which it selects whether to warm up a function on a high-end cluster or a low-end cluster or no warm up at all. In this way, we design the algorithm of IceBreaker's placement decision maker. Now let us discuss some of the key results that we obtained from IceBreaker. And IceBreaker was evaluated with serverless benchmark suite following the production workload trace from Microsoft Azure from the ATC 2020 paper of Serverless in the Wild. The main sets of results are from a cluster of 10 high-end servers and 18 low-end servers. First of all, compared to the state-of-the-art techniques like fast cache from ASPLOS'22 and Serverless in the Wild from ATC 2020, IceBreaker reduces the keep alive cost by 45% and service time by 27%. Note that the computing techniques here are originally designed for homogeneous clusters, but for the sake of comparison here, we made them heterogeneity aware. The keep alive cost benefits occur mainly due to IceBreaker's intelligent tier choosing by the placement decision maker, and the service time benefits come from IceBreaker's well-designed function invocation predictor. With its FFT-based invocation prediction, IceBreaker is more effective in adapting to frequently changing patterns and predicting the concurrency degrees, as we see from here that it converges much faster than ARIMA, which is a technique that is used in the Serverless in the Wild paper from ATC 2020. Service time of a serverless function consists of the execution time, the cold start time, and the wait time that the serverless function incurs before its invocation. We see that most benefits of IceBreaker comes from the reduction in the cold start time and the wait time, as IceBreaker is intelligent enough to correctly predict function invocation along with its concurrency degree. From the CDF here, we can see that the trend is true for most of the serverless functions. And this trend is not only valid for the average values, but it is seen in most of the serverless functions in our benchmark suite. We experimented with different types of high-end and low-end servers with different cost ratios, and the benefits of IceBreaker is prevalent in all of them. Also, a lot of serverless functions are hard to predict. That is, their invocation concurrencies are irregular and harder to represent mathematically. Also, some functions are very infrequently invoked, making them also quite hard to predict. IceBreaker's benefit in reduction of keep alive cost and service time is also more than the competing techniques in these two cases, all thanks to the intelligent placement decision maker and the function invocation predictor of IceBreaker. To summarize, IceBreaker is the first work to exploit heterogeneity in server node types to reduce the keep alive cost and service time in serverless computing. IceBreaker solves the problem from both service provider side and customer side. It introduces the state-of-the-art novel FFT-based function invocation prediction mechanism for frequently changing function arrival patterns, hard to predict functions, and varying levels of concurrency degrees. IceBreaker is open sourced and you can access it from the barcode given in this slide. Thank you for your attention.